Hi, welcome back. In this video, we're going to learn some more properties of determinants, talk about why some of them are true, and then we're going to end with another major theorem and how to use it. Okay, so first of all, the determinant of an identity matrix. Remember, an identity matrix is a square matrix that's a diagonal matrix. It has only ones on the diagonal. And we know how to get the determinant of any diagonal matrix. It's just the product of the diagonal entries. So the determinant of any identity matrix is always going to be 1. What about transposes? So say we know the determinant of A and we want the determinant of A transpose. Well, to get the determinant, we take a row expansion or a column expansion, cofactor expansion. Well, a cofactor expansion along a row on A transpose is the same as a column expansion, cofactor expansion along a column in the matrix A. So you end up with the same determinant. So the determinant of the transpose is the same as the determinant of the original matrix. Remember, determinants are only defined on square matrices. All right, so what about elementary matrices? Remember, an elementary matrix is a square matrix that's the result of a single elementary row operation performed on an identity matrix. So one of those operations is a row swap. And we know on any matrix, when you swap two rows, the determinant of the new matrix is just minus 1 times the determinant of the old matrix. So if we do a row swap on the identity matrix, the determinant of that new matrix is just negative 1. What about when you add a multiple of one row to another row? So here it says C times row K added to row L is the new row L. So adding a multiple of row K to row L, that doesn't change the determinant. The determinant is the same. So if we do that to the identity matrix, then we get a new matrix, but the determinant is still 1. All right, the last row operation is multiplying a single row by a scalar. So C times row K is our new row K. So what you're doing is you're changing it by that scalar. So the determinant of the new matrix E is going to be C times 1, or just C. All right, so we have our first major theorem about determinants. The determinant of a product of two matrices, based on what we know about elementary matrices and the determinants that we get, we can show that the determinant of the product of two matrices, A times B, as long as they're both square matrices, is the determinant of A times the determinant of B. Another major theorem that we get is the determinant of a scalar multiple of any matrix. We've actually already seen this. A scalar multiple of a matrix means you're multiplying every single row by the same scalar. So if A is n by n, you're doing that n times, and so the result is k to the n times the determinant of the original matrix. All right, now our third major theorem is actually the biggest one, the most important one. A square matrix A is invertible if and only if its determinant is not 0. This is huge. This gives us a lot of information about matrices and about linear transformations, which we'll learn about later in this course. So this theorem is so important that I'm going to show you the proof, because I think this is the type of proof every linear algebra student should be able to understand and possibly write a proof like this. So it's an if and only if statement. So that means it's these are two equivalent things. A is invertible is equivalent to the determinant of A is not 0. So you have to prove two things. You have to prove if A is invertible, then its determinant is not 0. And then also you have to prove if the determinant is not 0, then its invertible. So let's break it down and do it step by step. So the first piece of the proof is if A is invertible, then its determinant is not 0. That's called the only if part. So we start with assume that A is an invertible square matrix. Then that means that A times its inverse is the identity matrix. And by one of the previous theorems we had, we can say that the determinant of A times A inverse is the determinant of the identity, which is just 1. Well, so we can break that up and say it's the product of their determinants by one of the previous theorems. So the determinant of A times the determinant of its inverse is 1. Well, that means that the determinant of A cannot be 0, because if you multiply 0 times something else, you're not going to get 1. All right, so that part was short and sweet. So let's do the other direction, the if part. If the determinant is not 0, then A must be invertible. This is a little bit longer. So let's assume that the determinant of A is not 0. Now, using Gauss-Jordan elimination and remembering that we're using elementary row operations, we know that A is row equivalent to some square matrix B, and B is in reduced row echelon form. Now, because B is a square matrix, in reduced row echelon form, if it has n leading ones, so it's an n by n matrix, so if there's a leading one in every single row, then it's going to be the identity matrix, right? The reduced row echelon form of A will end up being that identity matrix. But if it doesn't end up being the identity matrix, it has fewer than n leading ones, then there's a row of zeros at the bottom. In reduced row echelon form, either you got n leading ones, which means you got the identity matrix, or you have fewer than n leading ones and you have a row of zeros at the bottom. Well, we know that the determinant of B would be 0 if it had a row of zeros, right? And that would mean that the determinant of A, because the determinant of A is just going to be some scalar multiple of the determinant of B, because we just did some elementary row operations on it. So that would mean the determinant of A would have to be 0 if its reduced row echelon form had a bunch of zeros, a row of zeros at the bottom. So we know that can't be true because we assumed the determinant of A is not 0. So that must mean its reduced row echelon form is the identity matrix. So it's row equivalent to I. That means A is invertible. So this is such an important theorem. We're adding it to a theorem we've seen before, but we haven't used a lot. So this is called the major theorem of linear algebra. It's a list of equivalent statements, equivalent conditions. So if A is a square matrix, then the following list of statements are all equivalent. What that means is that if one statement is true, all the other ones have to be true. If one statement is false, all of the other ones are false. So we've already seen the first 5. If A is an invertible matrix, then those other 4 statements have to be true. If the system AX equals 0, that homogeneous system, doesn't have just the trivial solution, it has infinitely many solutions, then A cannot be invertible. So all of these statements are true, or all of them are false. We've already seen this one, this list. We're now going to add a 6th statement that the determinant of A is not 0. That's equivalent to the other 5 statements. So if you have a system of linear equations, homogeneous or not, and you know that the coefficient matrix is invertible, then you know the determinant of that matrix is not 0. But even more useful, if you know in advance the determinant is 0, then you know you don't have a unique solution for every B, AX equals B. So it either has infinitely many or none. Let's look at a specific system and see how that works. So here we're given a system. It's a 3 by 3. x1 plus x2 minus x3 equals 4. 2x1 minus x2 plus x3 equals 6. 3x1 minus 2x2 plus 2x3 equals 0. This is a non-homogeneous system. So the question is, does it have a unique solution? It's a yes or no question. Well, we're going to use this major theorem here, and we're going to check the determinant of the coefficient matrix A. Writing down the coefficient matrix. Now, taking the determinant, I'm just going to expand along the first row. I get 1 times negative 2 plus 2 minus 1 times 4 minus 3. This is a cofactor expansion. Minus 1 times negative 4 plus 3. And when I work that out, I get 0 minus 1 plus 1, which is 0. I get a 0 determinant. So the sixth statement on our list is not true. So that means all the other statements on this list are false. So number 2 is false. AX equals B has a unique solution for every B. No, that can't happen. Either this system is inconsistent or it has infinitely many solutions. We just say no because the determinant of A is equal to 0. The answer is no. All right. We're going to see later this semester, there's 2 more equivalent statements. We're going to add the number 7 and number 8 later on in the course. But we're going to be using all of these statements. The determinant of a coefficient matrix for a linear system is extremely useful. All right. I'll see you in some other videos.